Syzygy, episode 13. Tiny energetic messengers from Blazar far away. Welcome back to another episode of Syzygy. We had a little bit of a break. We've had a break over the last couple of weeks. You may have noticed, you may not have noticed. Yeah, we had a bit of a week off. And the reason we had a week off is because, Emily, you've been cavorting overseas. Whereabouts have you been?
I have. I've been gallivanting. I've been over in Denmark, in Aarhus.
It's not exactly overseas, really, is it? I mean, we're in England.
It's literally over a sea.
It's over a sea, but,
it counts. It counts.
In coming from Australia, where everything is over very large oceans, it kind of feels cheating. It feels like you could almost walk it. You know, couldn't you?
Might take a little while, though.
All right, but Denmark, I mean, it's a nice place. What were you doing in Denmark?
It is a very nice place, and I highly recommend a visit. However, I was there on work, business this time. I was at the Task 4 meeting. So TASC is the TESS Astroseismic Consortium.
Now,
so these are the people who are interested in pulsations and stars who are also interested in TESS.
Yes. Now, those of you who've been listening to us for a while, from the very beginning will know that we do get pretty excited about a very small but very exciting spacecraft called TESS. TESS is the Transiting Exoplanet Survey Satellite.
Yes.
And how's it going?
She's going brilliantly, actually. Yeah, so it was very exciting. We had the project scientist from NASA who's looking after TESS, a guy called George Ricker, come and talk to us about the updates. So we got the insider scoop on how TESS is going.
Now, TESS launched, around about the same time that we launched this podcast, actually.
Yeah, 90 days ago today.
Wow, excellent. Oh, they grow up so fast, don't
they?
they?
Yeah.
And so it's still in the testing and pointing it at things and checking out that the pictures are all coming in.
Yep.
Tickety-boo. And it's all working well?
We're still testing.
Oh, God. How many times did that one come up at the conference?
Quite a few.
Yeah.
So anyway, the quote from George is that the resonance orbit that's been achieved by TESS is phenomenal. And this is, they don't use words lightly in NASA. Right, for these things.
I mean, this is an organisation that does phenomenal things on a daily basis. So when they get excited, it's going pretty well. And a resonance orbit? What do you mean?
Well, actually, Syzygy was
Funny
mentioned.
You should ask.
So TESS is in this orbit where it sort of comes quite close to the Earth and heads out to the orbit of the Moon. So there are times when it does actually have a Syzygy with the Earth and the Moon, which is very nice for us on this podcast. So the orbit is amazing. Actually, they reckon the orbit's going to be stable for more than 25 years, which is really exciting. So we could have a very, very long-run mission.
And the notion of resonance, it can be in this really interesting orbit, playing off the gravity of both the Earth and the Moon.
Yeah.
To be able to do interesting things without constantly, having to fire its retro rockets and things like that to get into position.
Exactly.
It's
so it uses very, very little fuel at all. So in fact, the fuel usage just to get it into orbit was so low that even with the fuel usage, they're expecting at least to 2028 for the mission. So.
Wow.
So cool. So
it's all going well.
Yes. So the orbit's all good. We're happy. And we're now testing the instruments, the cameras, seeing how they're going. We have our first light image, which came out a few weeks ago.
Yeah, we talked about that on the show, and I think I put the picture up in the show notes.
Yeah.
Lots of stars.
Well, I have some stats on this.
Hey, okay.
So in this picture, we have more than 250,000 stars.
Shut the front door. That's crazy.
It's amazing. I mean, when we think about what we kind of compare TESS a little bit to, which is Kepler, which was looking at about 100,000 stars in the whole mission, then 250,000 stars in this one picture.
Wow.
Which is not even a full frame from one of the 4 cameras. If you do sort of work out what the area of the sky that TESS is going to look at, this picture maps out to about 1/400th of the entire field we're going to look at.
It's staggering. I mean, it just really hits home how little we see here from the surface of the Earth. That even on an incredibly clear starry night where you think, wow, the sky is full of stars. No, you've seen nothing until you get up there and look through one of these suckers. It's amazing.
But what I didn't realise at the time is that you can go out and look at one or two of the objects that are in this image.
Oh.
And you can see them from the ground. So the very, very bright star at the bottom of the image
I'm looking across the office at your computer screen right now.
Yeah.
Yep, I can see it.
So this star is, this is in the constellation of Centaurus. So the star in the image is Beta Centauri. So one of the bright stars you can go and find and have a look at. And the bright emission nebula that you can see there, and the dark stuff is a part of the Coalsack Nebula, which is, so you need to be kind of southerly-ish, at least equatorial or below. But these are familiar parts of our southern sky that I'm sure Chris and definitely I am quite familiar with.
Yeah. I mean, as we all know, you see the best skies from the south, don't you?
Yeah. So the Coalsack Nebula is just in the side of the Southern Cross.
Very cool. So all go for Tess. It's all looking good.
Yes.
When do you expect to actually start getting real data that you can play with? Because that's the most exciting part.
Yeah,
right?
well, we're still testing everything. It is, I have to say, it is going amazingly. We've got data compression is working at twice as good as we were expecting it to
That's
happen.
always good.
So we're going to get a lot of data very, very quickly, which is very exciting. So we're expecting maybe the first data release to be in mid-December.
Right. So that gives you a few months to get properly excited and hyperventilating in anticipation.
So we haven't quite chosen what the first field is that Tess is going to look at. That's yet to be determined. But as soon as we do, you can bet that astronomers all around the world are going to slew their telescopes over and start having a look and see what we can see at the same time as Tess.
Hurrah. Well, at least we now know what to get you for Christmas, and that's a lot of caffeine, because you're going to need it to get through that first lot of data. Well, that's a little Tess update, but that's not the body of the show today. We want to talk about, well, some really, really tiny things. Some of the tiniest things that we've ever discovered ever in the history of discovering things, and that's neutrinos.
Neutrinos.
And in particular, one specific neutrino that winged its way through almost the entirety of the Earth back in 2017, a few months ago, before pinging off an atom or two deep down under the ice in Antarctica that happened to be within a detector block called IceCube. And it was set up to try to detect these neutrinos, which are coming from far, far away with very, very high energies, in order to learn something about the mystery of these neutrinos and where they're coming from in cosmic rays. So we're going to talk a little bit about that, because we touched on this in the last podcast.
Yeah, we did a fantastic job of preempting this discovery, actually.
We did.
Yeah.
It's forming a whole new way of doing astronomy, where rather than just collecting light or radio waves and seeing what you can figure out, you're bringing in all sorts of different tools, using all sorts of different kinds of astronomy, different particles, different entire fields of physics and astrophysics, in order to figure out what's going on. So we'll be having a bit of a chat about that. So in order to get into that subject properly, Emily, what's been going on? This has been in the news. What's the story?
So amazingly enough, we have found one single neutrino, which we're going to explain why that is incredibly significant and how one single neutrino can change the world. But this is for the first time in a very, very long time, in more than 20 years, that we've been able to work out exactly which astrophysical object this neutrino came from, and it's a new type of object.
It's such a cool story, because it's bringing in so many different things. And just to really hit that home, we are talking about one particle, one subatomic particle, like not one kind, one singular neutrino, which got detected down at the IceCube detector at Antarctica, which is a whole other subject that we can natter on about for hours. But it was this one thing that got detected, which makes it sound a little bit like neutrinos are incredibly rare, but they're not.
They're really not.
They're really, really not. So we need to talk about that a little bit. But let's back off to take the broader picture on this for a second. A neutrino has been detected that has come from a long way away. It's an incredibly energetic neutrino, and we've managed to figure out where it's coming from. So why don't we start with that? Where has it come from?
So it's come from something called a blazar.
Now, we've talked about quasars before. We've talked about pulsars before. Blazars we haven't touched on. That's a new one. So what's a blazar?
Well, they're not really a whole new thing. They're actually very similar to some of the other things we have talked about. So we've talked about quasars, which are very distant galaxies that have a really huge supermassive black hole in them. We call them kind of AGNs, or active galactic nuclei, feeding black holes, huge amounts of energy, all this really, really exciting stuff.
Yeah, incredible amounts of energy. And before it was figured out what they were or what they might be, these incredibly large black holes in the center of galaxies far away. They were called quasars because we didn't know what they were. We just needed a name for them. Really energetic things.
Quasar stands for quasi-stellar object.
Ah, okay.
So something that kind of might look a bit like a star but really wasn't. And then it turned out to really not be a star.
I mean, it looked like a star because it was bright, but it was only when it was realized how far away they were that it was realized just how bright these things were. It'd be a little bit like saying, oh, what's that over there? Is that someone who's got the light on their phone? No, that's a supernova on the other side of the galaxy. Incredibly bright things far, far away. And it turned out that they were huge black holes spitting out enormous amounts of energy in galaxies far, far away. So that's quasars.
Yep.
What's a blazar?
So blazars are pretty similar, except they vary quite rapidly in luminosity and brightness. So they can vary on timescales of, say, minutes or sometimes up to years. And what we understand now that a blazar, at least some of the physics that's linked to what a blazar is it's probably, we're looking at a quasar, or this big black hole that's feeding, but we're looking at it from a very specific angle. So it's this jet of material that's being fired up away from the pole of the black hole. And it just so happens that we're looking straight down that jet.
Right down the barrel of it.
Yeah.
Yeah. So why would that mean that we're sort of seeing it coming and going, like the intensity of it is changing over time?
So as the black hole's feeding, we've actually talked about feeding black holes in a previous episode as well. As it feeds, sometimes you get infalls of matter, so you get sort of splurges coming out through the jets, different changes and fluctuations in luminosity, therefore, and different changes in the amount of particles that are being produced.
So every once in a while, it sort of gobbles up a big bit of stuff and then burps out a whole bunch of energy, and we see that as a blip on our screen at the other end. But this is different from a pulsar kind of idea, which is where you've got not a black hole, but a rotating neutron star spitting out a bunch of energy, and that blips past us at a very regular rate. Similar kind of thing in that we're in the path of this beam of energy coming out of the black hole, but it's not rotating around, blipping past us. We're just seeing a variation in terms of its feeding schedule, as it were.
Yeah, exactly. And they're obviously black holes in the centers of galaxies are huge, huge, huge things, whereas pulsars are kind of like a single star.
Right. So a blazar isn't, you were saying a second ago, it's not a new phenomenon. It's something that we had seen, and we're now realizing, hey, we've seen that before, just in a different way.
Yeah, so our best model is basically quite a lot of these phenomena, which include quasars, blazars, something called Seyfert galaxies, which are kind of very active galaxies. There's actually an idea that they might all be the same thing. We're just looking at them from different angles.
Right. They're all galaxies with really huge black holes that are doing interesting things, and we see those interesting things in different ways. And historically, we've given them different names, but hang on, no, it's all really just the same thing.
Yeah.
Yeah.
Maybe.
Okay.
At least that's what we think for now.
So that works. So why is this particular blazar in the news then?
Well, it's the neutrino, really, that's changed everything. So in the past, we think that lots of things, they're very, very highly energetic, produce neutrinos. But we've only ever detected for sure neutrinos that have come from the sun, the center of the sun, and from one particular supernova 30 years ago, more actually.
Only two sources of neutrinos. So let's back up a little bit. We'll talk a bit about where neutrinos come from, right? Neutrinos are tiny, tiny subatomic particles. They're not even subatomic. They are fundamental particles, and they come from nuclear reactions, a particular kind of nuclear reaction, right?
Yeah.
In the nucleus of an atom, when you have a nuclear reaction that, for example, turns a proton into a neutron or a neutron into a proton. That's a kind of reaction that can take place. And in the process, a tiny little, almost insignificant particle gets spat out. That's known as a neutrino. And these were discovered decades ago. But it took a really long time to discover them because they barely interact with anything. They're really, I was reading in a paper today, someone described them as they're really snobbish particles. They don't like interacting with anyone. So it took a really long time to actually tell that they were there at all, because the only way that they interact is through these incredibly short-range nuclear interactions. They don't feel electromagnetism, so they don't have electric charge. They are incredibly light, so they barely have any gravitational influence on anything. And at that scale, you're not seeing gravity terribly much anyway. They barely see anything at all.
It's all kind of tied up in the name, really. There's two things that are important about neutrinos. And so neutrino, the word, encompasses those. They're neutral, so the neut, and the trino, which is they're tiny.
Yeah. It's a diminutive Latin, isn't it? The neutrino, which is really kind of cute.
Yeah.
But they are produced in copious amounts by the sun. There are an enormous number of nuclear reactions going on down in the core of the sun, which are spitting out countless numbers of these neutrinos. We should be seeing them all the time, except that they are so hard to interact with that you've got billions of them passing through your body right this instant. And in your entire lifetime, you might have one of them interact with an atom in your body. Maybe.
Yeah. So I've got a nice quote here about how small they are from Rains. And he says, they're basically the most tiny quantity of reality ever imagined by a human being. I mean, so we know that things like electrons are little, right? We know that atoms are small, electrons are smaller, but these things are so small, we can't even measure their mass.
Yeah, I mean, it took decades to even figure out that they had mass.
Yeah.
And it's still not even clear exactly how much mass they've got.
Well, we know that there's 3 types of neutrinos. They come in what we call flavors, and they're named after some of the other particles that they kind of have a mirror image of in the standard model of particle physics. So they're called electron neutrinos, muon neutrinos, and tau neutrinos. We didn't actually know that 2 of those existed, and for a very long time as well. But all we know about their mass is that if you add up the mass of each of those 3 flavors, then you're looking at something that's smaller than a billionth of the mass of an electron.
Yeah, it's crazy. I mean, these things are tiny.
And that's all we know.
But add to that, further to that quote, add to that they don't have an electric charge. Because the thing that makes the electron such an important and useful particle, not only in making up atoms, which frankly, if they couldn't do that, we wouldn't be here, but also in things like, being able to create electrical current to run our computers and laptops and everything, is the fact that they have an electric charge. And that electric charge allows the electromagnetic force to have an influence on them, and we can move them around and do all sorts of stuff with them. And that's an incredibly strong force. Neutrinos don't have that.
No.
So the only thing that they've got is an infinitesimally small amount of mass, which is not going to do anything with gravity. Gravity is utterly, irrelevant at this scale. And this kind of nuclear interaction, which is known as the weak interaction or the weak force, which is such short range and happens so rarely that billions of these things stream through us constantly and we don't even notice it.
Yeah.
They are almost not there.
So most of atoms are a kind of empty space.
Yeah.
So how you can kind of imagine this is that the neutrino is so much smaller than an atom. It doesn't even really see the components of the atom. It just wings its way straight through atoms, which means it wings its way from, say, the center of the sun, where it's being produced, all the way out to the surface without interacting with anything.
Yeah, and then comes across the distance between the sun and us, and straight through us, and straight through the Earth, and out the other side, and off across the universe, and seeing nothing the vast, vast majority of the time. There are countless numbers of these things, and it took us decades to even figure out that they were there at all. But if you set up a very clever system, big, buried deep under the ground so that you can, ignore effects from other kinds of particles that might get in the way. If you create a large detector which is sensitive to these kinds of interactions with neutrinos, and you sit there and wait long enough, you can actually detect them. And you can find them. And that's what's been built down in Antarctica, down at the South Pole, in this thing called IceCube.
Not after the rapper.
Not after the rapper, no. Although, that's kind of cool too. But this thing's amazing, isn't it?
So it's a cubic kilometre of ice.
Just think about that for a second. So that's a kilometre along a side, which is huge.
Therefore, it's a very, very large ice cube. Right?
Yes, yeah.
Now, you're going to take your cubic kilometre of ice, and I want you to put it another 1.5 kilometres underneath more ice.
Right.
So it's 1.5 kilometres down.
Yep.
Then you start your cubic kilometre of ice.
And what are you doing with the cubic kilometre of ice?
And we're going to fill it up with detectors.
Excellent. So drilling down into it and putting in these detectors, which are going to detect what? I mean, neutrinos, obviously, but it's a little bit more complicated than that.
Yeah.
It's not sort of, there's one.
No, they don't really interact with stuff. But sometimes, very, very rarely, they will basically smash into another particle and accelerate that second particle. And there's a nice effect called the Cherenkov radiation, which is very similar to a sonic boom. So have you ever seen a picture of a aircraft when it's going just a bit faster than the speed of sound? You get this big sonic boom and you get the big clouds and things.
Well, that's the sound equivalent of the wake behind a boat, right?
Yes.
A boat going along the water and you see that V-shaped wave coming off the back of it. That's a water equivalent of a sonic boom. And now you're talking about the sort of the particle physics equivalent of
which
the
is
wake.
a light effect.
Right.
So basically you get this big bright cone of light which tells you the original direction which the neutrino came in from. So it's actually what you're seeing is light produced by another particle, a muon usually. But what you can tell is that it must have been hit by a neutrino to cause all this light, and we can work out what direction that neutrino came in.
Right, you can reverse engineer it to say, okay, if it's this kind of reaction, then it was produced by this thing. And really importantly, in this particular direction, because you can see what direction that cone of light was coming from, and how much energy.
Yeah.
You can actually work out how energetic this neutrino was.
Yes, by how fast the particle is moving, how many detectors basically you hit off as the light goes past. And it's really important because actually a lot of these a lot of these events happen in our atmosphere. So you get cosmic rays, which can produce basically the same sort of effect, which is another reason why you would want to go deep down into the ice, because then you're protected a little bit from all these low energy interactions. And so you know that the ones that are actually entering into your telescope must have come from neutrinos that have passed through, in some cases, most of the Earth.
Yeah, I mean, that's the fabulous thing, is that this is a kind of telescope, but you can do it from any direction you want. You don't have to worry about, well, I can't point my telescope at the ground because the ground's in the way. No, that's fine. Neutrinos are going to come straight through the Earth and hit your telescope anyway.
And actually, you want those ones because you're really sure that they are neutrinos that have produced those flashes of light.
Yeah, so it's a really, really new and really interesting way of looking at the universe. So, IceCube last year saw a neutrino, and it wasn't just any neutrino, it was a really high energy neutrino.
It was a really high energy. So this is on the 22nd of September last year, and basically it started this flash that went through many of the optical detectors that are down there. So there's all these detectors are on these strings. There's about 86 strings that are in this cubic kilometre of ice. Each string has something on the order of 60 of these little detectors, and when you set off multiple ones of these detectors, you can then backtrack using time and both space coordinates to work out that it was a single neutrino and it came from that away. And of course IceCube instantly put out this alert that they found this interesting neutrino. I think
because they'd have computers set up looking for these kinds of patterns to be able to really quickly go, alert, alarm going off, flash the big red light. We need to tell people about this, because you then want to see if you can figure out, it came from there. What's up there?
Yeah, exactly.
Go and look at it with other kinds of telescopes.
So I think I read it was within 40 seconds this alert went out to all the relevant telescopes around the world. They all started pointing at this bit of sky. They refined where they were looking at. And a few days later, actually the detection was confirmed using a gamma ray telescope. And so the gamma ray telescope was looking at light, this very, very, very high energy light we call gamma rays. And the reason why it took a few days is because light is an electromagnetic thing. So it interacts with stuff in space as it travels, whereas the neutrinos, they don't care. They just come directly.
Barely see anything along the way at all.
Yeah.
So in this case, even though the neutrinos, have a tiny little bit of mass and they are going slower than the speed of light, they actually beat the light.
They beat the light
to it.
Yeah.
That breaks my head. I think that's really cool.
It is very cool. Yeah, so there's the team from Fermilab who basically run this ground-based network of gamma-ray detectors. They saw a spike that was indicative that this Blazar had indeed had a bit of a burp or had a bit of a flare, and that was matched up to the neutrino.
So this neutrino has been traced back for the first time. So there's a couple of firsts here, aren't there? It's been traced back to this Blazar. And so there's the first time that's happened using not only the IceCube detector, but a bunch of other telescopes. So that's a big thumbs up for this new kind of astronomy, bringing together all of these different different forms of detection. Remind me what that's called again? It's
Messenger.
Multi-messenger astronomy. So that's a first.
Yes.
But then, I mean, as you said before, we've only ever seen neutrinos from two sources out there in space before. One is the sun, and there are a lot of them coming from the sun. And the other was a supernova back in 1987 or something. We saw a bunch of neutrinos from that. So this is the first time that we've seen another extragalactic source and been able to pinpoint it as the source of that neutrino.
Yeah. So we can now say for sure that blazars produce neutrinos.
Which is really cool. And not hugely surprising, I wouldn't have thought, but it's a first.
No, but it's good to know.
Yeah, and what a great proof of concept for a brand new kind of astronomy to be able to say, no, seriously, we built this big crazy thing down at the South Pole. We buried a lot of stuff under the ice. But seriously, look, it works. We saw a neutrino and it came from that thing up there. I just think that's awesome.
It's really cool. And if it makes you feel a little bit better, they did go back and check the previous years of data. So IceCube has been running at full capacity since 2011. So we have some few years of data now. And
just to be clear, this isn't the only neutrino that IceCube's ever seen.
No. They get on the order of 70,000 every year.
Right, okay.
But they're not all real astrophysical neutrinos. A lot of them are atmospheric, and some of them are just bits that come from, say, the sun or other nearby objects that haven't really been identified as exactly that particular direction in the sky. So once they had this very high energy one, they were able to say, okay, were there any more that came from that direction that maybe were just a little bit too low for our normal systems to pick up and say, whoa, there's something going on here.
That didn't set off the big alarm bells.
Yeah.
Yeah.
And they did find basically what they call an overdensity of neutrinos in that direction. So there's more neutrinos coming from that piece of the sky than other pieces of the sky. But they weren't enough, and they weren't high enough energy to trigger kind of their own alerts. But they found 13 plus or minus 5. One of the biggest, definitely the biggest telescope actually that we have in the world today looks at just a few interactions every year, which is quite amazing.
Absolutely staggering. But it's reminiscent of that other really big new astronomical technique that's come out in the last couple of years, which is gravitational wave astronomy, where turning that one on and almost instantly detecting this incredibly small shift in their detectors, which signaled the collision of two black holes a very, very long way away. But we're still talking incredibly small amounts of data, incredibly slow rates of detection.
As opposed
to the hundreds of thousands of stars that are in Tessa's field of view, for example.
Yeah, but this is what happens when you push the boundaries and do new things in physics. I mean, we weren't 100% sure we would be able to see these kinds of things with these detectors. So that's what makes it so new and exciting as well.
What an exciting time to be an astronomer. I envy you. So that neutrino was discovered months ago, back in what was it, September 2017?
That's right.
So it's just become news now. I'm assuming that's because they've only just announced that they've worked it all out, having put together observations from a number of different kinds of telescopes and worked back through the data from IceCube to say, yep, we're absolutely sure now, or pretty sure, that it came from this direction. And if we look in that direction, then there's this thing, this blazar. That's why it's in the news now?
Yeah, so there were 2 papers that came out in the journal Science, and one of them was from the IceCube team, where they talk about this detection of, first of all, the first neutrino, and then going back and checking their old data and actually saying, oh, look, if you cut it this way and you look at this direction, then actually we have found some more that have come from this object. And the other paper was the link between the detection and the gamma rays, and the Fermilab team were working with IceCube on that one as well.
Right, and the two of them put together allowed the astronomers en masse to be able to say, that one up there, it's coming from this place, we're pretty sure, and it's a blazar.
Yeah, and that place happens to be the left shoulder of Orion.
Oh, well, there you go.
Yeah, so it's actually from a blazar. Do you want to know the name?
Yes, of course.
Well, it has this very nice name.
I'm sure it's got a really good name.
Oh, it's a great name. TXS 0506 plus 056.
I mean, even by astronomical standards, that's getting ridiculous. But there we are.
Yeah.
There we are.
Yeah, a lovely blazar, just a mere 3.7 billion light years away.
Well, it's, on cosmic scales, that's modest.
Middle-sized distance, maybe? Yeah, so it was in the top 50, if you like, of gamma ray sources.
On the charts with a bullet.
But maybe sort of in the middle to bottom, so it wasn't maybe the most exciting blazar. But actually, it might have been in this case that we see a neutrino from this object because the direction is really important. IceCube is most sensitive to neutrinos that come from celestial equator, so near kind of near the Earth's equator, equatorial regions. So this blazar happened to be there, so it increased the chances that we were going to see this thing.
Very cool. Okay, so what does this mean then? It's one of the things we like to do on this podcast is to try to bring it back around to, but that's all fun. So what? So throw it back to you, Emily. So what?
So what? Well, these neutrinos are one of the most fundamental building blocks we have in the universe. So we have a regime we call the Standard Model of physics. And this has a kind of a list of all the different subatomic particles, what they do, what their partners are like. And
it's the building blocks and instructions for assembly, really, isn't it?
Yeah, it's like the little Lego bricks. And you get some of them which have 4 dots and some of them which have 2 dots. And the neutrinos would be the tiny little one by ones, right?
1 by ones, but they come in 3 different colours. So
they come in 3 different
flavours, actually, strictly.
Yeah. And so the way we build up our understanding of the universe requires on us understanding the fundamental building blocks really well.
Right, makes sense.
And it's only very recently we knew that neutrinos even have mass. We thought for a while they might be the solution to dark matter. And it turns out that although there are an awful lot of them, they don't have enough mass for that. But, we need to learn more and more about these neutrinos and therefore the environments in which they're produced to be able to understand the construction of our whole universe, basically.
And I guess hence the interest in this one because, as we've said a couple of times now, this is the first time that we've seen one outside of the sun and that one supernova, and it's perhaps the beginning of a whole new regime of neutrino astronomy. Being able to see neutrinos and be able to learn about things that are happening in the middle of galaxies far away and all sorts of other really energetic events, being able to understand them from a whole bunch of different points of view, including from the sort of nuclear reaction neutrino point of view, which is brand new.
Yeah. And now we know what a neutrino from a blazar looks like.
Yeah.
We had no idea what it might look like before.
Didn't even know you could do that.
Yeah.
And now we do.
Now we've got a sample of 1 plus 13-ish that we can go and look at, and we can use that to help find more. Because once you know what you're looking for, it becomes much easier to find even more of them.
And that's it for another episode of Syzygy, the world's best astronomical podcast. We like to think so. Anyway, we had a little bit of a break, but we're back on a schedule again. Emily, good to be back.
Oh, excellent. So excited.
You're not going away again anytime soon, are you?
Yeah, soon. But...
Yeah, we might have a little bit of leave coming up, but that's all right. Listen, if you want to contact us on the show and submit a comment, a query, a question, I mean, the last time we had one of those, we based an entire show around it. So I think, it's a good thing to do. If you want to submit a question, there's a whole bunch of different ways that they can do that. Emily, how can people contact us?
Well, we're pretty active on Twitter. You might have seen some of the quick snaps from the conference last week. So if you check out at Syzygy Pod, so SYZYGYPOD.
Yes, and
then you'll find us.
If you're into your social media, then of course we do still have our still brand spanking new Facebook page. It's still got the wet paint on it, but you can find us by just going to Facebook and searching for Syzygy Podcast.
Yeah.
And there we are.
And chuck us a like.
Yeah, chuck us a like.
We like likes.
And we like to, we put up links to the show. We put up links to the show's YouTube channel. Yes,
Ooh.
a YouTube channel. Why would a podcast have a YouTube channel? Well, because apparently some people like to watch while they listen. I don't know. But the nice thing about it is that we, on the podcast, we like to put up, links to some of the pretty pickies that we come across that illustrate the things that we're talking about. Because astronomy can be a reasonably visual subject from time to time. And so if you watch it on YouTube, you can see those pictures coming up as well. Or if you want to contact us, you can just go to our website, syzygy.fm, and there's a little contact form there that you can just fling a message our way, and we'd love to hear from you.
Yep. Send us your hardest questions.
Yeah, absolutely. Make us hurt, because they're the fun ones, right? The other thing that we'd love you to do, we've had a few comments on the podcast and a few reviews on iTunes, Apple Podcasts, Google Podcasts. We're out there. You can go and find us. If you like what you're listening to, then do leave us a review. Hit us up for a couple of stars because it really does help other people to find us. And we'd love you to give us a review to hear what you think of us. But otherwise, that's it for another week. We'll be back again with some more astronomical goodness in about a week's time.
Yes, we'll see you soon.
Yes, indeed. Until then, ciao.
Bye.
My brain is not on today. I don't know if you've noticed. I just
tried that little switch. Just
turn it on and turn it off again. Just not with it. A couple of times I got into the middle of an explanation there and I was just going, I don't even know what I'm saying.
Words.
All the words. Let's start that one again.